Recording. There we go. All right. Welcome everybody to this Robotics Institute seminar. I am delighted to introduce our speaker today. Zackory Erickson is one of our newer faculty members here at the Robotics Institute. He, despite being new, has already been making lots of waves in the department. I see him everywhere. And so he's clearly been very busy. He runs the Robotic Caregiving and Human Interaction Lab, where I believe they have a hospital bed and a dummy to put on top of that hospital bed. Zackory's research is in building computational control and sensing methods to drive intelligent physical human-robot interaction. And one of his biggest application areas is in healthcare robots. He got his PhD from Georgia Tech, working with Dr. Charlie Kemp, and did some really interesting research there. And among several of his awards includes Best Student Paper from I-Corps. So with that, I will let Zackory tell us about his research.
Thank you for the intro, Henny. We see each other because our offices are not too far away. That's why we bump into each other all the time.
Everywhere.
But before I dive in here, if anyone has a question mid-talk, I know we don't really have that in-person body language of raising a hand, so feel free to just state questions that you might have over the mic. I won't mind at all, not a problem. Or if you have questions, put them in the chat. I'll try to touch on the question when I see it, either during or at the end of the talk. So for this seminar, I would like to share some of my group's ongoing research into this concept called haptic perspective taking, and how robots can infer haptic perspectives from both visual and force modalities. Now, my research group looks at robotic caregiving, the development of systems that can intelligently touch a person, apply force, sense, and manipulate both the human body and objects around the body. There was once a point in time where I had to justify why robotic caregivers could benefit society, but after we've all made it through 2 years of a pandemic, and after we've all seen news article after news article about staff shortages in healthcare, I think we all get the point. The potential benefits of healthcare robots is fairly clear to most of us. But I occasionally get asked, what is one of the core challenges in robotic caregiving? What is an unsolved problem that makes it difficult to deploy healthcare robots? And based on everything I've experienced thus far, my belief is that one of the core challenges in robotic caregiving is giving a robot the ability to exhibit common sense. Common sense can certainly mean a lot of different things, but in robotics, I'm really referring to a robot being able to recognize how its actions affect people. Essentially, a robot that physically interacts with people must be able to take actions that it knows with high certainty will be comfortable and will not hurt someone or put someone at risk. As an example of common sense, spoons belong in the mouth, not the eyes. That's pretty obvious to us, but it's not default knowledge for a robot. Don't pull cloth aggressively around someone's neck, otherwise we risk strangling them. Don't apply large forces to injured, sensitive, or weak parts of the body. Human caregivers don't do these things because they recognize the pain or discomfort it could cause to a person receiving care. But more generally, most people are able to recognize how their physical actions will affect others around them. What I'd like to introduce today is how I believe a concept called perspective taking could be a window into common sense among robots that physically assist people. And this talk is really going to focus on some of our past and ongoing research into this concept of perspective taking, but more specifically, haptic perspective taking. But I get ahead of myself a little bit here. First, I should probably touch on what perspective taking is, and then what do I mean by haptic perspective taking? So perspective taking is quite simply defined as viewing a situation or concept from an alternative viewpoint, such as from another person. For example, you might have heard of the phrase, put yourself in someone else's shoes. And This concept of perspective taking has been studied extensively in literature. Researchers have shown how perspective taking within humans and even empathy. In the context of caregiving and healthcare, dozens of taking, oh, I might be cutting out. How much of that did we just lose? That is very unfortunate. I'll try to continue though. So in the context of caregiving and healthcare, dozens of studies have categorized how perspective taking enables nurses and caregivers to exhibit empathy and improve the quality of care that they provide to those in need. And this is what I'd like to emphasize today, how perspective taking can benefit caregivers, but specifically robotic caregivers. Perspective taking helps human caregivers be empathetic and recognize how their actions affect someone receiving care, and robots could benefit from those same skills. All right, so perspective taking is the general concept of viewing a situation from an alternative viewpoint, and we know that humans can exhibit perspective taking. But what can this concept of perspective taking mean in the context of robotics? Well, within robotics, prior literature has investigated what is known as visual perspective taking. In this example above, there's two wrenches on a table, and the robot can see both of them. So if a person in this figure asks for the wrench, from the robot's perspective, it's not clear which wrench the person actually wants. But you might notice that the person can only see one of these two wrenches. A box, in fact, is obscuring sight of the other wrench, wrench number one. So if a robot takes a person's visual perspective, the robot can reduce this ambiguity and infer which wrench the person is likely referring to, specifically wrench number two. And visual perspective taking for robots has been investigated from several different angles in the past, building simulations of visual perspective taking for robots and people, visual perspectives through a mirror, and generating robot-based configurations that match a person's perspective. But just to clarify, visual perspective taking is also a capability exhibited by humans. And many of the same concepts researchers have developed into robots have previously been studied among people and through human-human interaction. But this then begs the question, what is haptic perspective taking? Well, inferring what a person experiences through their sense of touch. There are two ways of interpreting this definition. One is inferring the physical forces that are exerted on a human body that would cause a stimulation of our somatosensory system, our skin. The second would be inferring how someone cognitively perceives those applied forces. And for this talk, I'm going to focus on the former, inferring the forces exerted onto a human during physical interaction. Now, informally, in the context of robotics, we can then describe haptic perspective taking as, can a robot estimate the forces, both magnitude and location, that are applied onto a person's body during physical interaction? In the first half of this talk, I'll introduce haptic perspective taking modules for robotic caregivers that use force and torque sensing at a robot's end effector. We develop these models in physics simulation, and then we evaluate them with real robots interacting with real people. In the latter half of the talk, I'll then introduce visual haptic reasoning, some recent work by one of my PhD students, which is a generalization of haptic perspective taking to visual modalities. So as you might have been able to guess from the previous slide, we're going to explore haptic perspective taking within the context of robot-assisted dressing. By doing so, we can ask the question of, can a robot estimate how cloth applies forces onto a person during dressing assistance? And it might be worth touching on what makes robot-assisted dressing an interesting domain for developing haptic perspective-taking algorithms. And I believe the answer lies in manipulation of highly deformable cloth. One, cloth presents some challenge in terms of modeling dynamics. We will be manipulating cloth around people. The cloth will be suspended in the air, it's going to be pulled and stretched, and it won't be quasi-static. Second, manipulating cloth around the human body results in very complex force distributions. As you will see throughout this talk, forces caused by cloth are not uniform. There can be dozens of simultaneous regions of contact, and a single action can change the forces across all of the regions. And then lastly, this is kind of related to dynamics. There is also a question of how do we represent and sense cloth? Cloth lies in an effectively infinite dimensional space. It can be moved, stretched, pulled in any number of ways. So we have to investigate some sensing techniques to capture this rich contact and force information. So to start us off, let's try to visualize what haptic perspective taking can look like in this context of robotic caregiving. We have on the left a PR2, and it's going to be pulling the sleeve of a hospital gown onto a person's arm. And on the right, we're going to be visualizing the forces the robot estimates this cloth is applying onto the person's arm in real time. Red is high force, blue is low force here. And in this specific example, the robot is performing these estimates using only force, torque, and velocity measurements from its end effector. And the question lies in how can a robot make these dense estimates of forces in real time? Well, let's try to formalize this a little bit. We want to build an estimator, a function f, that takes as input prior end effector measurements from a robot, and then estimates the forces across a person's body. And it's important to note here that this function does not have an explicit model or observation of the fabric. It's estimating force maps just from end effector measurements. Now, this can be really neat since it does simplify the problem greatly, but later on in the talk, I'll touch on a potential downside of not observing cloth and a solution we've been investigating recently to overcome this. And again, the measurements are going to be coming from a robot's end effector. This includes haptic and kinematic measurements, force, torque, and velocity. And we're going to be getting this data using a force torque sensor, which is connected to the fabric garment, which the robot is also holding. And as output, we should expect a force map similar to this one being visualized here. But in order to estimate the forces exerted by deformable cloth, we need some way to model cloth dynamics. And for those of you who are familiar with deformable manipulation, you're well aware that we just don't have closed form analytical models for real world cloth yet. So we're going to need some environment that allows us to model cloth. Another challenge that we face is actually capturing these forces applied onto the human body. Our somatosensory system, our skin, it's a wonderful sensor for us as humans, but it doesn't provide robots any data. We can't just hook up a wire to our epidermal layer of our skin and capture measurements from our own mechanoreceptors. So we need some environment or sensor that allows us to capture this data. So to overcome these challenges, back in 2016, we built a physics simulation environment, which allows us to simulate how fabric applies force onto the human body. Here we have a robotic end effector pulling on the sleeve of a hospital gown onto a simulated human arm. And the colors on this represented on this arm are a force map where blue, again, is low force, red is high force applied at the arm. Internally, this physics simulation environment has a ton of parameters that have to be optimized. For example, there's a frictional value that ranges between 0 and 1, so it has no real world relationship. And so what we do is we actually collect data of a linear end effector pulling different types of cloth along the human body. and use all this data with an optimization method specifically called CMAES to optimize a bunch of the parameters of the simulation environment so that hopefully we're getting realistic forces and torques at the end effector, and of course, applied across the human body as well. And with the simulator, we're able to capture haptic and kinematic measurements from the simulated end effector due to cloth dynamics, and we capture the resulting forces applied by cloth during manipulation. Now, these force maps, they look continuous and smooth over the arm, but they have a discrete representation underneath. So let's briefly look at that, since it's going to impact how we learn these force maps. To start, the human arm is going to be discretized into 300 force sensing points. You can think of these as little force sensors scattered all over the arm. A vertex on the deformable cloth mesh will make contact with the simulated body at some arbitrary position X. It's going to apply some force F. And then we're going to distribute the magnitude of that force to nearby points along the limb. And if we were just to color the force sensing points based on the force applied at each one, it would end up looking something similar to this. And then finally, what we do is we just perform an interpolation across all these points to generate a nice smooth force map along the arm. Now, if we come back to our estimator, we're going to have this 9-dimensional input measurement at each time step, the 3-dimensional force, torque, and velocity data. But more importantly, the output of our estimator is this 300-dimensional vector of inferred forces across a human limb. Now, in terms of implementing this estimator, we do so using a recurrent neural network, but there are certainly other types of architectures and temporal networks that would work here. What I believe is important is to have some model that leverages temporal features, since manipulating cloth is a highly dynamic process, and estimating how the cloth is interacting with a person's body relies on information from past cloth states. Now, since we have a simulator, we train this recurrent model on thousands of dressing trajectories where the robot moves around randomly in a self-supervised fashion with the goal of collecting lots of data of how fabric interacts with the human body and applies force onto a person. But unfortunately, if we try to naively use this model, we get some really weird scenarios like this, where the trained model is estimating these tiny forces all over a person's limb. This is just regression error. The model is constantly estimating these small forces all the time. Now, we could just implement a fixed threshold where all forces below the threshold are zeroed out, but I would argue there's a little bit cleaner of a way to do this. So to overcome this problem, we build a contact map, which our model will also estimate. And just like the force map, the contact map is going to have 300 points, one for each corresponding force sensing point on the limb. And this contact map is going to be set up like a binary classification problem, where for each point on the arm, it's going to be assigned a value of 1 if the cloth is applying some non-zero force there. Otherwise, the contact map will be assigned a value of -1. Then if we bring this back into our model, we're now going to be estimating both the force map across a person's body, but also this contact map. So a 600-dimensional vector, all concatenated. And what we do after performing an estimate is that we loop through all of the forces in the force map and zero out any of them in which the contact map indicates that there's no force being applied. So this is going to allow a robot to estimate both how much force is being applied by this deformable cloth, but also if force is being applied at specific regions along the body. Now, I won't spend much more time talking about simulation because I too want to start discussing real robot experiments, but I'll just point out that this learned model does work when evaluated in simulation. And this first instance here, the hand and forearm are going to go into the sleeve of a hospital gown, where we see our estimates shown on the left are closely matching the ground truth forces from simulation on the right. And in the second instance, the gown is going to miss the hand and just get dragged over the upper arm. And the paper for this work presents other evaluations and discusses some extrapolation capabilities of this model to variation in end effector trajectories and velocities and arm pose and such. And we can also apply this learning-based technique to other tasks with deformable fabric, such as pulling a pair of shorts onto a leg. And here, the shorts are getting caught on the heel of the foot and starting to tug and apply force there. But so far, everything we've talked about has been entirely in simulation. And like I was, you're probably thinking, is this actually going to work in the real world? Is a robot able to infer the forces that real cloth applies onto a real human body? So let's talk about some recent and ongoing work of ours to evaluate haptic perspective taking in the real world. We take our estimator model that's trained in simulation, and we're just going to drop it onto a real PR2 robot and evaluate it. And to start off, let's look at how we can validate force map estimates using a real world force sensing array. What we do here is we wrap this fabric capacitive force sensing sleeve around a mannequin's arm. The sleeve has 210 distinct force sensing taxels. You can see it on the grid structure of these taxels in the figure on the right. And we also position a PR2 robot right next to the mannequin that's holding an assistive tool and hospital gown. And as you will see in some of the videos in the following slides, we had this robot pull the hospital gown over the mannequin and force sensing sleeve using various linear end effector trajectories. But before I show some results, I should discuss a small tweak in the measurement x sub t here. If you recall back to our estimator, our measurements consist of just these local force, torque, and velocity readings. However, this estimator, as originally defined, doesn't really have the capability to generalize across different human arm poses, since it has no observation of human pose. So what we're going to do is adjust that here. We include an observation of the 3D position of 3 joints along the arm, the wrist, elbow, and shoulder. And these 3D positions are visually inferred using IR reflective markers along the limb. This is going to help just mitigate any pose estimation errors. And note here that a robot will be pulling a garment over the arm, and these points are going to become occluded. So we rely on an assumption that the human limb will remain static. So in this first evaluation, we see the robot pulling a sleeve around the forearm and having it tug and pull at the elbow. And for the most part, we are observing that the estimated forces are, at least for this talk, qualitatively matching the forces measured by the force sensing sleeve. However, you probably noticed a few scenarios here that look like this. Our estimator is inferring some force applied at the hand, whereas the force sensing sleeve doesn't sense anything. This is a limitation of our current wearable force sensing array technology. The hospital gown is definitely in contact with the hand. Our estimator is correct here, at least qualitatively, but the force sensing sleeve cannot measure these very small normal forces or frictional tangential forces. If you happen to have a better sensor for this, please reach out to me. I'd love to chat more and try to address this problem. But for this talk, this is just a limitation worth being aware of. So here's another example. Oh yeah, question.
I'm assuming the robot has a wrist force torque sensor.
Yes.
And can't you use the constraint that the wrist force sensor force has to equal the spatially integrated force on the arm? And
absolutely you can. Absolutely
that would force it into a particular mode where, hey, I snagged on something.
I agree. You absolutely could. So there is, I think for the PR2, this specific end effector doesn't have a wrist mounted force torque sensor. You definitely could though. I think the other arm does have one. Part of the reason why we, so I think there's potentially 2 aspects to this question. One is why we use a force torque sensor on this assistive tool here. I think part of it is just to try to better align the force simulation that we had at the time to the real world environment where the force torque sensor was really, kind of at that point of contact between the robot and cloth. And I think the other aspect that you mentioned maybe is that, can you just use something like just directly the force torque readings at a force torque sensor to manipulate cloth around a person's body? Do you even need to, maybe your question is like, do we even need to do haptic perspective taking? Can we just use the raw measurements? I agree at the same, I also agree that that's definitely possible. And I think the idea here is that we're really looking at, trying to estimate where specifically, not just the general notion that forces are being applied to the body, but where specifically those forces are applied to. And so that's kind of where haptic perspective taking, I think, fits in. Hopefully, does that answer it? I had two different interpretations of what that question could be, so there was two answers.
I don't question haptic, whatever, to viewpoint taking or whatever you call it.
Yeah.
I'm trying to figure out what additional sources of information could help you get that more accurately estimated. Another source of information is looking at the cloth.
Yes.
And when you snag on something, you'll see it increases and things like that.
Absolutely. So at the end of the, maybe not the end, the latter half, we have some ongoing work and recent work actually looking at that, of including some other sensing modalities, vision. Because of that, right now there is no observation of cloth. We really have no context of, in this, like this specific video here, we have no context that the cloth is getting, it's getting caught on the hand. Haptic perspective taking gives us some insight into that, but at least from like a raw sensing modality, we don't have that information yet. We can though, I definitely agree with you. We can get that information. I'll touch on it a little bit. And I think there probably are other sensors that we can add into this as well. So yeah, you mentioned, wrist mounted force torque sensor. There might be other haptic sensors that could be applicable here. I have some other work on capacitive sensing that also might be slightly relevant in this context. So I completely agree. Multimodal sensing is important. We've been trying to work towards that, but there's still a lot of work to do in that space. Great. Yeah, thank you, Chris, for bringing that up. All right, so as this video shows, we've already talked about it. So I think I can probably move on, but that the cloth gets caught on the mannequin here, and we estimate high forces on the fist. We measure those, also similarly high forces on the fist. And just one more example where the garment slides over the entire arm. We again see our trained estimator is inferring the right spatial distribution and magnitude of forces applied by this deformable garment. So we can numerically evaluate our estimated force maps using wearable force sensors, but there's also a human element at play here. Do people actually perceive the robot as being able to estimate the forces applied to their body? So we conducted a human study with 15 able-bodied participants in which a PR2 pulled a hospital gown sleeve over a participant's arm with various trajectories, and we visualized the force maps for participants in real time. And the figure on the right here shows what that experiment setup looks like. And what we do is we evaluate human opinions on 3 different estimators. The first being our estimator with human pose as input. Second, an estimator without human pose. And then finally, as a baseline, an estimator that replays a random previously recorded force map. And so we test out 4 different human poses during the study, and all the various trials that we run are randomized, I should say, to remove bias. And so here's one trial from the human study where the cloth gets caught and applies force kind of underneath of the forearm. And the right visualization shows the estimated forces from our estimator that was trained from human pose, trained with, I should say, human pose observations. And we correctly observe forces applied on the under part of the forearm, as well as near the shoulder. Here's another example of this where the cloth misses the forearm and slides along the outer edge of the arm. Interestingly, if we remove human pose information from the estimator, the robot is not able to infer how this cloth is interacting with the human body correctly. Even though the cloth slides along the outer edge of the arm, the model just thinks all the force is applied at the hand. And after each trial, we had participants provide an answer to a single statement. The visualization matched what I felt in my arm. And participants responded on a scale of 1 through 7 on how much they either disagreed or agreed with this statement, where 1 is I strongly disagree and 7 is I strongly agree. The visualizations did match. And what we found is that participants overwhelmingly agreed that the force maps generated by our estimator aligned with what they physically perceived through their sense of touch, with a median score of 6 out of 7. And rankings are much lower for an estimator without human pose and for a random estimator, which suggests that people can also perceive differences in estimated force maps. So what I've described is still an ongoing investigation, but early indications are that a robot is able to estimate how cloth applies forces onto the human body. Now, can we use this signal to inform control? Could haptic perspective taking enable a robot to help someone get dressed? And the way we're going to approach control here is looking at how to predict future force maps that would result from executing a proposed robot action. Doing so will allow us to optimize robot actions to minimize future forces. So if we come back to our estimator, we're now going to be forming another model, a predictor, which is essentially a dynamics model. And this predictor G will take as input prior measurements from the end effector along with a set of proposed future actions. And along with this, we will be trying to output a set of predicted future measurements that a robot could expect to see if it were to execute those future actions. And here H sub P, that is the prediction horizon, which is how far into the future the robot is looking. We can then feed these predicted measurements into our already trained estimator, and voila, we are now predicting future force maps. Of course, we can start to do function composition where we have f of g. This allows us to go directly from robot measurements and future actions straight to a predicted force map across the body. But one question you might ask is, why split this problem up in the first place? Why have 2 separate models? You know, a separate estimator and a predictor. Why not just go end-to-end, one whole model? Well, you certainly could go end-to-end. You could just train one model. I suspect that would work just fine. Yet one reason for splitting this up is that we can stack these models and predict further into the future without having to do any model retraining. So here's just an example of that. We can pass the output of our predictor back into our predictor, and this will allow us to predict twice as far into the future. So now if we piece together our predictor with the estimator, we can predict force maps across a person's body that a robot could expect to observe if it were to execute candidate actions. The predictor is going to have the same network architecture that we used for the estimator. In fact, we can even train the predictor on the same data we use to train the estimator. And the way we're going to use this predictive model to control a robot is via model predictive control, or MPC. So for those of you who are not familiar with MPC, it's pretty simple. We're going to pass a lot of different types of actions into our predictor, and then we're just going to select the actions or the set of actions that minimize the predicted forces from the output. But to formalize this a bit more, what we will actually be doing is selecting the best future actions that minimize some cost function J. And here's that specific cost function that we used in our method, which has 3 different terms to define what is the best action for the robot to take. The first term minimizes the predicted forces across a person's limb. The second term encourages the robot end effector to be moving along the limb, to be making task progress, essentially helping someone get dressed. And then the last term discourages the robot from rotating its end effector whenever possible. So that's it to this controller. We then conduct a human robot study with 10 able-bodied participants in which a peer-to robot use this control method to dress on the sleeve of a hospital gown. And what we found is that if we prevent the robot from looking very far into the future, the robot doesn't recognize that it's applying large forces onto a person's body until it's it's already too late and it's starting to tug and pull at the elbow. Yet by increasing the prediction horizon, the robot recognizes that it can continue to minimize forces by rotating around the elbow and pulling this garment all the way up to a person's shoulder. And the robot successfully pulled a garment up to a person's shoulder in almost all the trials that we had tested with the participants. And similarly, by preventing the robot from looking very far into the future, the robot doesn't recognize that a garment is about to get caught on a person's hand and apply large forces until it's already too late. The garment has gotten caught and it's starting to tug and pull on the person's hand. Yet by allowing the robot to predict further into the future, the robot is able to recognize that a garment would soon get caught on a person's hand. It then lowers its end effector closer to a person's body, shown here by this red line. And this allows the robot to mitigate the garment from entirely getting caught on a person's body. Now, recall so far, we've been looking at estimating and predicting force maps using mostly just haptic data from a robot's end effector. It's pretty neat that we can estimate high dimensional force distributions with just low dimensional haptic measurements, but the approaches we've discussed so far do face some significant limitations. First, the models have very limited information about the human body or pose information. Previously, these are just 3 joint positions. The models only estimate a fixed dimensional force map at predefined locations along a human limb, and it's difficult to scale this approach to whole body force estimation, which would be ideal since during dressing assistance, cloth is interacting with the entire human body. There's also no direct sensing of the cloth, so generalizing to other garments may be unlikely without retraining. And then lastly, there's no spatial context or recognition of what the cloth is actually making contact with. If you replace the human body with just some random object, the model would have no idea. And these are some of the core challenges that we've been working to overcome in a recently submitted article by one of my PhD students, Yufei Wang, who is co-advised with Dave Held. And this has led to our work on visual haptic reasoning. Can a robot reason about a person's haptic perspective using visual sensing? And our approach to this centers on inferring the forces that cloth applies onto objects using just a single depth image perspective. So what this is going to look like is that at any time step, we're going to capture a single point cloud of a scene from a depth camera. This point cloud will include points that are both on a deformable cloth that is being manipulated, as well as points that are on some contacting object, such as the human body. And we're going to feed these, this single point cloud observation through a haptic reasoning model. And this will be trained in simulation, and this model will output the magnitude of forces applied at points along the human body that are undergoing contact with the cloth. So let's break down how this is actually going to be built up. If we come back to our estimator, we're now going to have a model that takes as input a point cloud from the scene and then estimates the forces at points along the body. Notably, unlike our previous approaches, this function now does have an explicit observation of fabric. But let's go a little bit deeper into how do we do this estimation. Given some scene or scenario of cloth in contact with the human body, we're first going to capture a depth image from a single external depth camera. We then convert this to a point cloud using the camera's intrinsic matrix. And then this, as a next step, we're going to separate this into 2 distinct point clouds, one representing the human body and another for the cloth. In simulation, this operation is pretty trivial to do. In the real world, we can do this using visual segmentation, such as color segmentation, to get a rough approximation of this split. But with those of you with a keen eye might notice there are some points on the human point cloud that are not observable by the depth camera. The points in this orange circle on the top right should not be there based on what I've described so far. However, the way we capture a complete human point cloud is that we actually capture a point cloud of the person before a robot starts pulling cloth over the body. So there's no occlusions yet. We can see the entire human body before we start manipulating cloth. And we can use this initial point cloud of the person to overcome visual occlusions that occurred during dressing assistance. But just so you're aware, this again relies on an assumption of a static human pose. So now, given point clouds of cloth and a person and some kinematic information of the robot's end effector, we're going to train a model that estimates the applied forces at each point along the human. We also have some flexibility in how we formulate this estimation model. And I'll show two different architectures that we've introduced thus far using either Pointnet Plus or a graph neural network. And I'll talk more about how these models are structured in a moment. But if you recall from earlier, we had to develop this contact map to zero out small regression errors that would recur when making force estimates. We're going to do the exact same thing here. We're going to train a separate contact estimation model, which again just estimates whether a point along the body is undergoing contact with cloth. And so at this point, let's start to dig in what these models actually look like, starting with a Pointnet Plus implementation. For clarity, the contact and force estimation models here, they're virtually the same. So just to simplify things for this talk, I'm going to just walk through the force estimation model. So Pointnet, for any of you who are unfamiliar, is a neural network architecture for interpreting 3D point cloud data with applications ranging from object classification, part segmentation, to scene semantic parsing. And an improved design of Pointnet called Pointnet Plus was also introduced in 2017. And what we find is that the segmentation branch of a Pointnet Plus architecture can be used to estimate the forces that cloth applies onto other objects given a dense point cloud observation of a scene. So now Pointnet Plus consumes point clouds directly. So all we need to do is define a feature vector for every point in that point cloud. So for each point, this feature vector is going to consist of first, the 3D position of said point. Second, a one-hot encoding of the point type. So whether this point is on the human, on the cloth, or part of the robot's gripper. And then lastly, the three-dimensional velocity of the robot's end effector. And once we form this feature vector for every point, we're just going to pass it all through a Pointnet Plus model, which will then provide an estimate of the force applied at every point in the point cloud. And we're going to keep just the estimates along the human body. And during training, we can then backprop estimation errors through a Pointnet model to update the learned weights. So Pointnet Plus is one implementation of turning point clouds into force estimates. Now let's look at another way that we can model the same problem using a graph neural network. Starting with a point cloud, we need to form some graph G consisting of vertices and edges. The vertices are fairly straightforward. We're just going to set all of the points as the vertices. Now, in terms of the edges of our graph, though, we're going to form two different types of edges. So if we zoom in on just a couple of vertices in our graph here, just as an example, we have some points that are on the cloth colored in blue, and some other points on the human, which are colored in orange. And we first form edges between all adjacent cloth points that are within some distance threshold of each other. That would look like this in our example graph. We then form some edges between cloth and human points that are adjacent, and that would look a bit like this in our example graph. And in order to hand this graph over to a graph neural network, we also need to define features for the vertices and edges. So each node in the graph will have a one-hot encoding of the associated type. This can be human, cloth, or robot gripper, as well as the three-dimensional velocity of the robot's end effector. Yet to make this graph translation invariant, rather than providing the global 3D position of each node as a node feature, we instead defined 3D displacements and Euclidean distance as an edge feature between every two adjacent nodes. And with that, we now have a graph. We can pass that through our GNN to infer the applied forces at each vertex in the graph that's associated to a point on the human body. And as you might have suspected, we trained both the Pointnet Plus and GNN models in a cloth simulation environment. We have a robot end effector represented by a point mass that grafts onto different types of cloth and pulls this cloth along the human body and using a set of random trajectories. And one of these tasks is assisted dressing, another one bathing assistance, dishwashing, and pulling cloth over this set of primitive shapes. So during simulation, we record point clouds and the associated forces applied onto the object by the cloth. We randomize the shapes and sizes of the human body and other objects, and we also use a variety of types of cloth, including washcloth for bathing and plate cleaning, a hospital gown for dressing, and a small blanket to pull over these primitive shapes. And already, without looking at any evaluations yet, we can already see that there's going to be a number of potential benefits in this new formulation of haptic perspective taking. We can estimate forces across an entire visible human body surface now, rather than just predefined limbs. We can now train models on a wide distribution of human body shape and size, which allows us to model to model how cloth interacts with people that don't fit a 50th percentile body size. And one of the benefits of using models trained on point clouds is that since the model receives a direct observation of the cloth, there's an opportunity for these models to generalize across different forms of cloth. So let's look at a couple of rendered examples of what performance looks like in simulation. Here's a dressing task using a trained Pointnet Plus model as the cloth is being pulled along the top surface of an arm. And for the most part, the estimated force maps are aligning with what we are observing as ground truth from the simulator. And in a few slides, I'll provide a bit of quantitative evaluation of this performance. Here's another the same dressing task, but now we changed the human body size quite drastically. And we find that the same Pointnet Plus model is also able to generalize force estimates to other body sizes. Here's another demonstration, now this time with the trained GNN model. And again, the cloth is going to get caught on the hand and apply large forces there. But we also see that the cloth slides along the person's leg, and we're able to infer that contact now as well. And lastly, a quick example of our model inferring the forces applied by a deformable washcloth as it's pulled along a simulated human arm. The model correctly infers that the highest forces are applied near the end effector and the forces dissipate outwards around the cloth. We also evaluate the performance of these models quantitatively on a held out test set and compare performance to a few baselines. If we look at the mean absolute error in force map estimates, we find that both the GNN and Pointnet Plus models achieve similar performance for dressing, bathing, and dishwashing tasks. And in addition, these models perform at least twice as well as just a standard multi-layer perceptron or even the best possible constant force estimator. And we also have a model, if you can recall, that does contact estimation, estimating what points along the body are or are not in contact with cloth. So we can also evaluate that model too. And using an F1 score metric here, we again observe similar performance between the GNN and Pointnet Plus. In this case, the Pointnet is slightly better for inferring binary contact. And comparing to two baseline methods, we again see decidedly better performance with our models. We then set up these same environments from simulation in the real world with a mobile manipulator for bathing assistance or for a bathing assistance task. We have the robot following predefined trajectories along the arm of a medical mannequin that's lying in bed. For dressing assistance, we are again pulling a hospital gown sleeve along a mannequin's arm. And then for dishwashing, we have a plate on a table in front of the robot. In each setup, you're able to see the external camera that we use to actually capture depth images of the scene. And it's worth noting that the camera angles used in the real world are different from those in simulation, just to add a bit of a challenge. So in this first case, the robot attempts to pull the hospital gown sleeve onto the arm of a mannequin. The sleeve gets caught on the hand, applies large forces there along the hand, but we also see some smaller forces along the forearm and near the shoulder as expected. Here we see a mobile manipulator wiping a washcloth along the arm of a medical mannequin in bed with force estimates from our Pointnet model. And finally, an evaluation of the dishwashing task with a washcloth where predictions are made from a GNN model. And you'll notice that as the cloth runs along the edge of the plate, we see higher forces since the surface area of contact decreases. And again, the end effector doesn't actually make contact with the plate here. This is distribution of contact that's made entirely by this deformable washcloth. Now, if we go all the way back to the beginning of this talk, common sense. It's a crucial challenge for robotic caregiving, and hopefully after all of this, you can see why I believe haptic perspective taking can be a window into common sense, enabling robotic caregivers to reason about how their actions will physically affect people that they interact with. Of course, there's still a lot to do towards this goal, such as better leveraging of haptic perspective in a feedback control loop, multimodal sensing, and in general, just more evaluations in different assistive contexts. But our early work in this path has been providing some promising outcomes. And with that, I'd like to thank you all for attending. It's always fun to share this research, and I'd be happy to take any questions. Awesome. Thank you all. I see one hand from Wenjen.
Hello, Zackory, great talk. Have some thought of when you talk about the work. So one is
Absolutely.
that you're thinking about like it's hard to get the ground truth about where the cloth is contacting the human hand. I think one possible solution is that you can make a soft robot platform of the arm. And I do have some previous work on detecting the proprioceptional sensing, like overall shape deformation of the arm, which can potentially cover a large area, so that you can set up internal cameras and using our methods to detect like the deformation on the surface. So I think that that should be feasible, although it could be a painful process to build a system.
Yeah, I do like that. The kind of the thought is that we have maybe this some sort of like translucent silicone body, right, of a mannequin, and then we put in these I'm thinking based kind of like based on the gel site, right, we put in different cameras inside of the mannequin itself to try to estimate those applied forces. I think that would work.
We can check out chat offline for like the details.
Yeah, that sounds neat.
Some other alternative thought. I was thinking about that if you can probably use vision or other method to detect the stretch of the fabrics, which could be an indicator about like where is the contact. So for example, I saw you're playing with simulation. Actually, if you're tracking the motion of the point cloud, and you can track like whether there's some like stretch of the point cloud on the surface. So that can give you some ideas about where is the contact. Another thing is that you can, if you work with the real environment, you can find some cloth that is largely deformable. And you can set up background colors and the foreground color of the cloth. So when the cloth is stretched, the color actually changes. So you can use a camera to capture the change of the color.
Yeah, I like this. In the area of deformable manipulation in robotics, there's actually been this has been an ongoing challenge of how to track cloth stretching, and yeah, so I really like these different types of ideas. One of the challenges with using a point cloud is that it doesn't inherently track cloth stretch. If the cloth stretches, your point cloud gets bigger, but there isn't necessarily a mapping from point to point. In simulation, we can cheat. We can use like an internal like cloth mesh and just track points over time. But yeah, I definitely agree. In the real world, it's tricky to track stretch, but if we had a method for doing so, I also agree, that would be very informative in terms of like the dynamics of cloth, how it's interacting, amongst itself, self collisions and things, but also how it's interacting with other objects or a human body in the environment. Yeah, great point and question. I like it. Thank you.
Thanks.
I see another hand up. Oh, do you have anything else, Wenjen?
I know, I will leave time to other people first.
Thank you. I see another hand up. And I also see a question in the chat. Curious about the strategies used to control the force applied to prevent the subject from being hurt by the forces applied to them. What would you like to know about the control method? Anything in particular you're looking for or curious about?
I'm just interested to hear whatever you have to say on it. I'm a little bit newer to some of this, so I'm just like wanting to get your perspective.
Yeah. So we used, let me see if I can pull up the slide. I'm not sure how long it would take. We used mild predictive control to do this. Let me click through here. So there's a whole other types of controllers. Actually, continuing on visual haptic reasoning, we are looking at, what are the other types of control methods? So we've looked at mild predictive control, but there's definitely other controllers that would be relevant here. So as you know, as an example, reinforcement learning is constantly described in literature nowadays, and there's a lot of interest in that. I think definitely reinforcement learning is applicable. How to incorporate this concept of haptic reasoning is an open question. We've started looking at that, but I don't have any concrete solutions to that yet. So those are some ideas. There's also, you could also consider approaches of, using human demonstrations, or, treating humans as experts and having demonstrations, having people actually perform these different types of tasks, tracking control that way, and, doing behavior cloning or inverse RL to try to also perform this type of task. So I think there's a lot of different types of control approaches. We've only looked at MPC so far. But hopefully within the next 6 months or a year or so, we're going to be investing in a couple other different types of control methods to do this. Hopefully that was a little informative, but good question. Other questions? I see some hands raised. Whoever blurts it out first goes.
I'll go first, I guess. Awesome research. It's such an awesome
Thank you.
thing to sort of target. But I had a question in regards to like disturbance. Like introducing sort of like motion artifacts to your simulations, because a patient, when I think of patients, I think of them not holding their hands very still.
Sure.
They might probably move or do something. Like have your lab thought about ways of integrating such like unpredicted artifacts, and like how would the robot, or have you thought of introducing it into your simulation and then having your algorithm predict how the robot is supposed to sort of tackle that, or is that like a futuristic thing at the moment?
Yeah, I love this question. It's maybe not that futuristic. I didn't talk about any of this in this talk, but I have some other work looking at what's called capacitive sensing. It's another type of sensing method that uses electric fields to sense the human body. And in that work, we actually, one of the core reasons for why we were looking at it is that there are many people that one of the reasons why they need assistance with dressing is because they have tremors, or they have difficult time moving their body parts, at least moving with high precision and such. So an individual with tremor, sometimes this can be quite significant tremor. And so absolutely, I agree, it is important. We have been looking at other types of sensing modalities to kind of sense that human motion, either small or big, large human motion, and how to adapt to that during tasks such as dressing, where there are visual occlusions. We haven't incorporated that into this work. I don't see any reason why it couldn't be, though. Another sensing modality, and I think moving forward, we definitely want to include more sensing modalities into this type of haptic reasoning. So I completely agree. That's a really great question. We've been touching on some other work I didn't show on this, and hopefully that could be incorporated into this type of this direction of research. Great question.
Awesome, thanks.
Thank you. Other question? I see 2 more hands. Either want to go? Victoria?
Yes.
Or Harp Lab?
I think Harp Lab was first.
Okay, go for it.
Sure, we can go. Cool. Thanks for the really interesting talk. I wanted to, this sort of builds on the last question a little bit, but sort of ask more about the sort of expected interaction between the robot and the human during the dressing process. So like, it's one thing to sort of get detailed models of force sensing, but in the context of the interaction, those models, the accuracy that you need for those models are different from what sort of leads to a successful dressing operation, right? And so I thought it was interesting that you brought up the idea of sort of the gown snagging on the elbow and getting pulled is like, this is a concrete thing that can happen if we don't have this sensing modality. And sort of, relating to the last question, a thing that is likely to happen is not just sort of random movements of the arms, but people could sort of move their arms to help the robot to, dress and sort of slide into place. So I was wondering if you could talk a little bit more about that kind of like, either the interaction component or sort of thinking of the problem at that level.
Yeah, so maybe if I interpret it correctly, or maybe if I reword it, could this be, what happens does the problem change, or does the formulation change if we have collaborative people, right, that are moving around? Would that be some interpretation?
Yeah. Ooh, there we go. Yeah.
Yeah.
Okay.
So I definitely agree. You know, one of the assumptions we make, you know, I try to, you know, is that we do right now, and this is, you know, just a limitation, is that we assume that a human is held static. That makes it a little bit easier for us to deal with these visual occlusions as we're developing these algorithms. But, you know, of course, in the real world, that's, I can't really think of many scenarios in which that actually would work in the real world, you know, making this assumption that a person is static. It's just natural for us as people to be, you know, dressing is a very dynamic task. We're moving around to get dressed. Even if someone is dressing you, if you have any motor function at all, you're probably moving around to make that easier. Unless, you know, unless you're really young, then you might be a little bit adversarial, but that's a different problem. And so I definitely agree with this. I think it's very interesting. You know, some of my previous work has been looking at how to sense and adapt to human motion during, you know, visual occlusions, and, you know, how to track that information. We haven't, you know, figured out exactly how to incorporate it in this context, since a lot of there's definitely we're kind of working towards it, but we haven't gotten there yet in terms of how do we break that assumption of assuming a static person, and, you know, someone who is dynamically moving around, collaborating with the robot, and how do we track forces over a body, an object that is moving around in addition to the cloth moving. So we haven't figured that out yet. Hopefully soon, but I'm curious to hear ideas if you have any. It's a really interesting question, and we've been starting to look at this, but we haven't gotten it yet. Yeah, thank you. Anything else on that, or another question, Victoria?
Hello, thanks for the great talk, Zackory. I'm looking forward to the adversarial child user study next. I'm curious how you set the weights for the MPC objective.
Oh yeah, yep, I definitely get this one. I skip over this. It's nothing fancy. Let me pull up the slide. Here we go. Click through this. Yeah, so these weights, honestly, it's hand tuned. There's definitely, there are algorithms that can do tuning of weights in MPC. We found that for the most part, hand tuning was okay, and realistically, most of the weight is actually falling in that first term of minimizing predicted forces. The other two terms are mostly just to add a little bit of signal in terms of what the task is. It's not just moving straight in a straight line. There is a little bit more to it, but beyond that, you know, it's mostly most of the weight falls in the predicted forces and trying to minimize those. Yeah, it's a good question. I think another aspect that, you know, some other researchers look at, I haven't looked at this yet, is, you know, one of the neat aspects of MPC is that you can change the cost function mid trial, really, mid robot execution. So you know, there's other researchers that, you know, have been looking at, you know, how do you have, using MPC, have a bit more dynamic, you know, either dynamic cost functions or dynamic control based on that. And yeah, so those are all, you know, possibly interesting ideas. Again, I think, you know, touching on another individual's question, MPC is one way of using this information. There are probably other ways as well. That was a long answer to such a simple question of how are the weights defined. Great.
There's a question in the chat from Mateo.
I see that. I can read it out. Hi, Mateo. Would there be any advantage in representing cloth and or bodies as meshes rather than as point clouds? Yes, there would be. My reasoning for asking this is that it might be easier to think about deformation as a mesh rather than deformations of individual points on a point cloud. Absolutely. In simulation, this is in simulation environments, this is really simple because we have meshes of here's that slide. So in simulation, we can actually define the cloth, yeah, exactly, as a mesh. If we're operating entirely in simulation, we can just track the points of the mesh. That's going to allow us to observe things like stretching and deformations, how much the cloth is bending. We could see all of that using just ground truth mesh information. If the real world cloth was also a mesh, or at least how we've currently representing this type of mesh, I think that would be the ideal case, right? Because then you can track how individual points along this mesh are moving over time, which you can't necessarily do. It's not entirely trivial how to do that with a point cloud. And so I very much agree. There would be a huge advantage to representing cloth as meshes. I think that there may be some works, there may be some work in looking at how to actually do that. But yeah, right now, the current approach that we have, and I would say, in deformable manipulation in robotics, kind of as a subfield, has mostly been relying on things like point clouds and such, which we can build. There is some method such as like garment net for trying to infer cloth mesh from point cloud information. So there's definitely some attempts at trying to do this. Yeah, absolutely, it would be great to do this. Checkerboard hospital gowns, yeah. So if you have a visual representation, absolutely you could, another work that was part of a collaboration is we actually put these, like little markers on cloth. And so you can actually, track, based on these, like physical markers on the cloth, you can track those kind of points. You can kind of essentially build a mesh in the real world based off of these physical markers. It's definitely the ideal case, but it does require a little bit of a challenge to build that mesh in the real world. Again, in simulation, very easy. Yeah, great. Thanks for the question. That's really insightful. I absolutely agree. And performance is usually better if we have something like a mesh representation of cloth. It's just a stronger representation in general, usually. Yeah, great questions, everyone. Anything else? I like the discussion. Yeah, if you have other ideas, I'm happy to discuss more externally as well.
Thank you, Zackory. We're all clapping. Thank you.
Thank you. Thank you, everyone. All right. Have a great day, everyone. Take care. Thanks for attending.